For existential quantification, the syntax will be, first of all, the operator, it will be something like this, right? Let me just write it down over here. For existential quantification, not this, right? It's like an alphabet E, not that. Like that. You gotta flip from left to right. So that's the so-called existential quantification. Quantification. And how do you pronounce it? Well, you can say there exists. Okay, that's how you pronounce it. Okay. All right, let's now go over some very similar facts about existential quantification. Okay, it's going to be a comma separated list over here, and notice that it's actually and over here, right? And to really, I'm not going to explain like justify by why one should be implication for the universal case, and one should be conjunction in the existential case. This might have been done maybe in your earlier math course. I mean, I'm not going to spend time, but if you want to know, you can feel free to drop by to reach out to me. I can explain that to you. That's kind of something you assume, but you can take it for granted for this course. Right? We're going to say the range must be true and the property must hold over here. Right? So very similar as before. X is a comma separated list of variables. R is supposed to specify the range or the type of the variable. And also property is something that we must satisfy, and it should be and over here, right? So there, how do we interpret that? So there exists a combination of values of all the variables listed over here, such that they satisfy both R, the range, and P, the property. Okay, if you can find at least one, so-called a witness. Let's take a look at some examples, similar as before. Right? If say there exists I, only one variable, so there's no comma just yet. So I is a member of N. So this is more like an R, specifying the range. And I larger than or equal to 0, that one is more like a property over here, right? So typically for the conjunction that you write for every existential quantification, you should really imagine that you should split them into two parts. One part is about the range or types for all the variables listed. And the right hand side should be all the properties you want the variables to really satisfy, right? All right, so we are saying that I should be a natural number and I is larger than or equal to 0, right? There's at least one I. Well, it should be true. For example, 5, right? 5 is a natural number, and also 5 larger than or equal to 0 is actually true. So true and true is going to be true. What about this one here? This one here, if I change this to be universal over here, that used to be false, right? Because we said -2 cannot be larger than or equal to 0 in the previous slide. But now we change that from universal to existential. Fundamentally, we're only asking about, is there at least one value of I that is an integer and I is actually larger than or equal to 0? Of course, for example, 5. Right? That's why it's true. So you want to compare and contrast these three predicates. The R and P are actually the same. It's just that we're using different logical quantification and also different conjunction, different connectors over here. Right? The next one. So we got multiple variables over here, I and J. Again, I is integer, J is integer. So this is the first part, okay, about R. And this part over here is the predicates for property. So we are saying that, so there's at least one combination of I and J, both being integer, I less than J, or I larger than J. Well, that's true. For example, since it's a disjunction, so I only need to make, you know what? I think there's a slight typo over here, right? Let me explain to you. That might be something which might be something to explain very quickly. Since I didn't include a slide about precedence of the logical operator, let me copy this part over here, and then let me explain that. Okay, this one over here is actually not exactly what I really meant to say, okay? Because you can see the logical operators we have over here. You can see we got here conjunction, conjunction, and disjunction, okay? We talk about the precedence of like an order of evaluation for logical operator. Precedence of logical operators. Okay, the one that actually that one ties the bounds the tightest should be negation, and then followed by conjunction, and then followed by disjunction, and also the if and only if, and also equivalence. Okay, so what does that mean? In this case, you can see we got conjunction, conjunction, disjunction. Because conjunction binds tighter, right? So it would be as if we actually put the brackets in this way. It would be as if we do it like that. And then we say, or I larger than j. But that's not exactly what I really meant to say, right? What I really meant to say is instead, this way here. So this is actually, so the blue one over here is how the predicates is evaluated, because conjunction binds more tightly than disjunction. Okay, so I think what I really meant to say was like this. Okay, I should have put a like a parenthesis. Okay, so what I meant to say was like this. I should really put this. Okay, if I do it this way over here, so that means this part over here is the R, the range. And then remember we got a conjunction, the connector in between, and then this part over here, the entire part over here within the parenthesis, so this part over here is the P, right? Right? The point is this one over here and this one over here are different, right? Because the order of evaluation is different. This one here is something or something overall, but this one here is something and something overall, so they are different. Okay, so when you actually didn't put any parentheses, you gotta be careful about how you would be as if bracketed, right? According to the precedence. Okay. So what I will do is I'm gonna fix the slides by including the parentheses around over here. That's what I will do. Okay, around here. So when you see the slide, it should be already fixed. But when you watch the video, you should really also see the lesson about precedence over here. Okay. All right. So this one here, assuming that we actually got some brackets over here, should that be true or false? Well, it should be true. Well, because it's disjunction, so I just need to find a combination of I and j that will satisfy one of them. For example, 3 and 5. Right? 3 is integer, 5 is integer, and 3 less than 5, true. 3 larger than 5, false. True or false is going to be true, right? So overall, it's going to be true. Let's now talk about proof strategies quickly, okay? And how do you prove that this existential quantification is actually true, the general form, right? Unlike the universal quantification case, in order to prove that universal quantification actually holds, you have to consider every element in the range and show that every one of them will satisfy the property, right? If they're in the range. But in the case of existential quantification, you only need to show one witness. And the insight will be, think about when will R and P actually true. Right? It's a conjunction. We talk about in order for the conjunction to be true, we want to make sure both operands are true, right? That's the only way for the conjunction to be true, right? When both are true. Meaning that the variable should be in the range, R being true, and also they should really satisfy the property P, right? So we should really give a witness of some variable list such that the range satisfy and also the property actually satisfied. Right? That's something we should do. And how do you disprove it? In order to disprove it, it takes a little bit more efforts, because somehow you want to show that there's no such witness to actually show the R and P are both true. So we want to say for all variables combinations, in that case R and P is always false. Right? That's basically what we have to do. So how can we show? So when will R and P actually be false? Either, well, in order for a conjunction to be false, either operand will be false, will do, right? In that case, either we can say the range is actually true, right? The range over here will satisfy, but the property actually is false. Or, even easier, if the range is already false. In that case, it doesn't really matter what the property is, right? So these are the two possibilities. So we can either say we show that for all the instances for x, it is the case that the range will, sorry, let me say that again. For all the x such that the range is actually satisfied. But for every one of them, the property simply does not hold. Okay? Be a little bit more careful. When I say not P holds, I really meant P will simply evaluate to false, right? Just be careful with my notation here. Another way to do it, which corresponds to this case over here, we simply show that the range over here is simply doesn't hold itself. For example, empty range. So you can never find a witness in the empty range for the variable, right? Right, so that's about a very detailed refresher about the universal versus existential quantification and also the proof strategy. Just keep them in mind. We'll definitely use them later. Okay. All right, so I got some exercises for you. I think I have said already many things for you to actually review. So I would suggest I'll leave this part over here as exercise for you. I got solution there, right? You can, let me give you a little bit overall overview about what you're supposed to understand from this example. For every one of them, you're supposed to look at the universal or existential quantification. And I said proof or disprove. You want to first of all decide intuitively whether the quantification should be evaluated true or false. In the case it is true, you want to prove it. In the case it is false, you want to disprove it. You can refer to the strategies which I mentioned in the earlier slides, right? I'll let you go over these examples yourself, right? To save a little bit of time for the lecture, okay? But if you got any trouble understanding any one of them, reach out to me. I'll be happy to help. All right, final slides about predicate logic is about how we can switch between quantification. I'm sure you have seen these before. I'm pretty sure you can read these two if and only if conversion from universal to existential and from existential to universal. But instead, I'm actually going to give you maybe an example for each conversion just to have more intuition when you study the conversion theorems. Let's now switch to the notes over here. And let's now go one by one. Okay, so we talk about conversion. Conversions. Okay. Between universal and existential from one way to the other, right? Let's talk about the first example, right? Let's say if I have the following for all, let's make something simple so it's easier for you to actually see the conversion. Let's say for every I, okay, such that I is in a particular set S. Okay, well, I don't know what S is, but it's some set. Let's say if I assert the following to you, I such that I is a member of S. It is, if I is a member of S, it is the case that I is positive, right? So what I'm saying is, for every I that's in the set S, I is larger than 0. So that's what I'm asserting to you. If I know that this is true, this will be true if and only if, thinking in alternative way, if every member in S is actually larger than 0, that means I cannot find any member in S that is not positive, right? That means I cannot find any, that means I cannot simply not find any elements in S that is not going to satisfy this particular property, right? Since it is not the case that there exist, you know what, let me just write all in the same color and then I'll highlight. Okay, that'll be easier for me. Okay, so it is not the case that I can find at least one I such that I is in the same range of S, and also not the case that I is larger than 0. Okay, so these two are actually saying the same thing. If I cannot find any witness such that there are in the range of S, and also they are not positive. If I cannot find such a witness, that means every one of them should be positive. All right. And notice the conversion over here. You need to put negation and change from for all to exists, and also you want to put negation to the property, right? Notice that. Of course, the same property that I intentionally keep the same over here, right? All right, let's talk about the second one. what if we start with existential quantification, and then we want to convert that into its universal counterpart? Okay, so what about number 2 over here? If I tell you that there exists, let's say I, such that I is in S, and also I larger than 0. Okay, I'm using similar example, right, just for simplicity. Okay, so this will be true if and only if. So this is saying that in S, I can find at least one number that's actually positive, at least one. Since I tell you that I can find at least one witness, that means it must not be the case that every one of them in S is actually not going to satisfy this property. Otherwise, you just cannot find a witness, right? So I'm going to say it is not the case that every I that's in S is not positive, because otherwise I just cannot find such I, right? They are really saying the same thing. Okay, so you can see again we are actually adding a double negation over here for both at the, outside and also for the property, and the property we're talking about is still I larger than 0. And then we also change from exists to universal, right? So just it's a very simple example just to show you how to really convert between. And I think the example I used is rather intuitive, but if you got any trouble understanding that, you can think about them a little bit more to convince yourself, or reach out to me. All right. Okay. And let's now go back to the slide to see if there's anything else to say. Okay. Let me just move them to here. All right. Let's now go back. Okay. Actually, that's the final slide for predicates, right? And let's now move on to talk about sets theory.